Teamwork. It has been essential to human civilization throughout history, bringing us such wonders as the pyramids and the Eiffel Tower, games like soccer and football, and advances in technology that led to, among other things, computer and robotics. I'm Tim Stevens, and this is my senior design project, MARRC, Multiple Autonomous Remote Robot Coordination System, the next step in robotic teamwork and cooperation. These robots are working together as a team to build a car. But what happens if the arm putting the roof on the car breaks? The arm building the side of the car doesn't necessarily know how to put the roof on the car, so we end up with a lot of unintentional, permanently open convertibles. MARRC solves this problem by ensuring that the system knows what needs to be done, so that if one part or robot breaks, the other robots in the system can take over and no work is lost. The current implementation is a cooperative mapping protocol with multiple robots mapping out an area. Although each is supposed to only map out its own area instead of the others for efficiency purposes, if one robot breaks, the adjacent robots will adjust and absorb the portions of the broken robot's area into their own. Considering the following secure building. A human security team monitoring the area would know not to cross each other's paths or end up with the entire team in one room or wing. A robotic monitoring protocol set to randomly patrol might not, and end up with a very insecure location. The solution is to make sure that no two robots are patrolling the same area, by making sure that each robot knows where the other robots in the system are. MARRC accomplishes this by using unique identifiers to guide the robots towards each other until they collide, as seen as in the middle of the hall in this diagram, thereby providing exact location data to both robots in the collision. Each subsequent collision can be daisy-chained so that even though two robots may never have seen each other, they can still be aware of each other's location as stored in the server. Here's the MARRC platform. It consists of an iRobot Create, a netbook, and a webcam. The configuration that will be shown in the demo uses the netbook's onboard webcam for vision versus the external webcam shown here. Communication with the iRobot Create posed the first big challenge of the project. Although it is a common robot development platform, there's no Java library available for communication with the platform that wasn't deprecated years ago or stored on a secure university server. So I created my own communication library using the iRobot Create open interface, which describes a protocol of operation codes and data to be sent via serial cable to the robot. For serial communication, I use the free open source Java library RxTX. Here's a video demonstration of two robots driving using the aforementioned driving library. And here is the MARRC server view showing the path data from those robots. Each robot needs to know where, or MARRC needs to know where each robot in the system is at all times. It does this by implementing a path tracker. Each MARRC bot sends distance and angle traveled approximately 10 times per second, which is converted to standard Cartesian coordinates and stored in the server. This gets more complicated when synchronizing the coordinate systems, as they each have their own individual coordinate system and no notion of a global system. Let me explain what I mean by individual versus global. If I tell you that I walk 10 feet forward and ask you to do the same, you would walk forward 10 feet, but not in the same direction that I did. This is because each person has their own notion of forward, backwards, left, and right. This is their individual coordinate system. To overcome this, humans developed a notion of north, south, east, and west. If I said I walked 10 feet north and asked you to do the same, we would both be 10 feet in the same direction from where we started. This is the global coordinate system. To create a global coordinate system for MARRC, when two robots collide, an algorithm selects which of the individual coordinate systems to keep and converts the other robot coordinate system to that one. As shown in the diagram here, the coordinate system on the left is stored and the coordinate system on the right is converted into the other system, as you can see on the diagrams in the left and right. For a human eye, even detecting which side of the robot is being shown on the top is difficult. Put it against a white background and it becomes even harder to find the outline, let alone which side is facing the camera. To make it very easy for robots to find and identify each other, QR codes were used. The very distinct pattern of a QR code makes it easy to identify in any image. The location of the QR code in the image is used to direct the MARRC bots towards each other. QR codes can also encode text, meaning that not only is it simple to detect, but by placing a QR code on the front, back, and sides of each robot, any robot detected can be notified that it has been seen and should turn a certain amount and look for a specific QR code, namely the front of the robot that detected it. The detected location of the QR code on each robot is used to center them on each other. If the code seen is too far to the left of the frame, turn a little to the left, too far to the right, turn a little to the right, and then update with a new QR location and repeat. Here you see a robot centering itself on a QR code in an image. Here's the server view from that code. The first dot, the red dots shown are the first laptop bouncing on the bump sensor, and second, the collision with the other robot. The bounce issue is fixed by repositioning and securing the laptop on the robot's surface. Here are the main information flow in the system. Everything shown is detected by the robot, then either stored locally or sent to the server for processing. Position update happens constantly and regardless of other events, short of the system being shut down. When a bump is detected, if a QR code has been seen recently, meaning since the last bump, that is interpreted as a collision with the detected robot and reported to the server as such. Otherwise, the position is marked as having an obstacle. In either case, after a bump has occurred, the robot will reverse, turn away, and continue along its random path. MARRC is the next generation in cooperation of robots. Its path memory and understanding of its surroundings enable it to use multiple robots working in a team to easily map and patrol an area. Although for this project it was only deployed with 2 robots in a small room, a large number of MARRC bots would be capable of any number of more complicated and impressive tasks.